Okay, part two of AC power factor. So let's go through these calculations here. So example number one tells us a series circuit consists of a 1.2 kilo ohm, so 1200 ohm resistor, and a capacitor of 0.1 microfarads. Supplied with 45 volts, so a series circuit, so resistor, capacitor in series with each other, supplied with 45 volts and the 1 kilohertz frequency. Calculate the apparent power, true power, and reactive power for this circuit. Okay, should be easy enough. The first thing we need to do is convert that capacitance into a capacitive reactance, which, remember, capacitive reactance is dependent on frequency. So we'll do our calculation. XC equals 1 over 2 pi of C. That's capacitive reactance of a capacitor, F being frequency, C being the capacitance. So we've got 1 over 2 times pi times 1000, that's my frequency, 1 kilohertz, times 0.1 microfarads, which is not shown in this equation, but we're obviously going to convert those 0.1 microfarads into farads, so it'll be 0.1 times 10 to the negative 6. So that should give us a result of 1.59 kilo ohms, or 1590 ohms. So 1590 kilo ohms, or sorry, 1590 ohms, 1.59 kilo ohms. So then now we have our resistance, which is 1.2 kilo ohms, 1200 ohms, and 1.5 kilo ohms is our capacitive reactance. I can use that to work out my impedance now. Why do I want to work out impedance? Well, I can't work out the apparent power without knowing what the impedance is first. So this equation here just represents the Pythagoras of my triangle, right? The R is one side, the X is one side, Z is my hypotenuse. So square root of R squared plus XC squared. If you remember this formula from our last module, you'll notice that we're only using XC squared because we've got no XL, there's no inductor in the circuit. So R squared plus XC squared, so 1200 squared plus 1590 squared, square root of that equals 1.99, 1990 ohms. In order to work out the angle, so those three sides there, so my 1.2 kilo ohms, 1200 ohms, 1590 ohms, 1990 ohms forms a triangle, and in order to work out the angle in that triangle, I'm going to go arctan. That's just another way of saying inverse tan. Inverse tan, capacitive reactance over resistance. Why capacitive reactance over resistance? Capacitive reactance will be the opposite side to my angle, and the resistance will be the adjacent side to my angle. If you think about that triangle, this is going to be opposite my angle, this will be adjacent my angle, so that's O over A. So inverse tan O over A, TOA. So tan to the negative 1, 1.59k over 1.2k gives me an angle of 53 degrees. So now I'd be able to draw that triangle if I wanted to. I've got my three sides, I've got my angle, away I go. The next thing I'll do is work out my current. Again, why do I want to know the current? Well, power equals volts times voltage times current. Power equals volts times amps. So if I want to work out power, it's going to be handy for me to know what the current is. So I equals V over Z. V in this situation is going to be my supply voltage. Z will be total impedance, right? Because if I want to work out total current, I need to know total impedance. So it'll be 45 over 1.99k, 1990, equals 22.6 milliamps. 22.6 milliamps being 0.0226 amps, or 22.6 milliamps. So the apparent power, V times I. So total voltage times total current. 45 times 22 milliamps equals 1 volt amp, 1 VA. True power will be volts times amps times cos of the angle. Why cos of the angle? Because this is going to form another triangle, my power triangle, and the apparent power will equal the hypotenuse of that power triangle. If the apparent power is the hypotenuse of that power triangle, then the true power will be the true power will be the adjacent side. So I've got an A and an H, so it's car, right? So volts times amps, that's my apparent power. So I go hypotenuse times cos of the angle, which is my car. Cos adjacent over hypotenuse equals cos times hypotenuse equals adjacent. Cos times hypotenuse equals adjacent. So if that's my hypotenuse, 1 times I times V, which is the same as apparent power, that's my hypotenuse. Cos of the angle times the hypotenuse equals the adjacent. 45 volts total voltage times 22, same as what we've got up here, because remember we're just doing the V times I, we're working out the hypotenuse again, times cos 53 equals 0.61 watts. Reactive power, I squared times XC. Now I could use I squared times R for this equation here as well, right? Because I just go current, I know what the current is, it's a series circuit, the current is the same everywhere. I know what the resistance is. The resistance was 1200 ohms. So if I do I squared, 22 milliamps squared times 1200 ohms, I'll get the same answer here. And here we're going to use it to get our reactive power. We could use trigonometry again, but it's just as easy to do this. This just gives you an example of different ways that we could do this. So I squared will be 22 milliamps. So 22 milliamps squared times 1.59 kilo ohms, that's was my capacitive reactance, equals 0.81 VAR. And you would find if you drew a triangle with a side of 0.61 and a side of 0.81, and then you measured the hypotenuse between them, that's going to be the apparent power will be your hypotenuse. So these three numbers here make up my power triangle. Remember, we have reactance, true power, and apparent power. All right, example number 2. A coil having a resistance of 6 ohms. Sorry, the little symbol there hasn't rendered properly, but that's going to be ohms. 6 ohms and an inductance of 0.03 henries is connected across a 50 volt 60 hertz supply. Calculate A, the current, B, the phase angle between the current and supply voltage, C, the power factor, and D, the apparent power. E, the true power, F, the reactive power. Okay, that's easy enough. So in order to work out the current, what am I going to do? Well, first, to get the current, I'm going to need to know total impedance of the circuit, aren't I? Of course, because my total current will be voltage divided by impedance. But to work out, to get my total impedance, first I need to know the total impedance is going to be the total of all the resistance and reactance in the circuit, right? So I need to know what my reactance, I've got my resistance, that's 6 ohms, but I don't have my reactance. All I've been told is that my coil has a 0.03 Henry inductance. So first I need to work out inductive reactance. Here's our formula here, 2 pi FL, F being 60, L being 0.03 henries. Note that this is not given in millihenries, it's in henries, so I can put that straight into my equation. So XL equals 11.31 ohms. I then use my Pythagoras, R squared plus XL squared equals Z squared, so square root of R squared plus XL squared will equal Z. 6 squared plus 11.31 squared, the square root of that is 12.8 ohms. I now have my total impedance, so I should be able to use that to come up with my total current. How do I do that? Oh, apparently we didn't bother. Oh, here it is at the bottom. Okay, I was looking for it at the top here. It's at the bottom. So to get my current, which was the first question, I equals V over Z, basic Ohm's law. 50 volts divided by 12.8 ohms. Remember, 12.8 ohms is our total impedance in this one here. 50 divided by 12.8 equals 3.91 amps. Easy enough. Next question was phase angle between the current and supply voltage. So I go, I'm going to use the inductive reactance and the resistance because there'll be two sides of my triangle. Remember, it doesn't matter if I did the impedance triangle or the power triangle, the angle would be the same. So inverse tan inductive reactance divided by resistance. So inductive reactance being the O, the opposite, and resistance being the A, the adjacent side of my triangle. O, so it's inverse tan O over A. 11.31 over 6, 62 degrees. Next question was the power factor. So the power factor is easy enough to work out once I've got the angle of the supply voltage. There's actually a couple of ways I could do this. So cos of the angle, cos 62 equals 4.69. Remember, it's also going to be the same as apparent power divided by resistive power. So resistive power, the true power divided by apparent power, or resistance divided by impedance. So in this case, my resistance was 6 and my impedance was 12.8. So if I do 6 divided by 12.8, it's going to be 0.469. But we've got that angle and we haven't worked out our true power, our apparent power yet. So the easiest way to do it would just be to go cos of the angle. Cos 62 degrees equals 0.469 rather. Okay, next question was now we've got to find the apparent power, true power and reactive power. Okay, that should be easy because we've worked out every other variable in the circuit and there should be heaps of different ways that we can do this. So apparent power, volts times amps first. So that's easy, right? Total power. Apparent power is the same as like total power, so total voltage divided by total current. Oh, sorry, multiplied by total current gives me 50 times 3.91. It's 195.5. True power, we've got S times power factor. Why? Because power factor is our ratio of true power to apparent power. So if I multiply my apparent power by my power factor, that'll give me the true power. What other ways could I do true power? I could do the same as what we've got up here. I could work out the voltage across the resistor and then multiply it by the current. I don't know the voltage across the resistor, that we haven't worked that out yet. But if I don't have the voltage across the resistor, well, what else could I do? Well, I know the current. That was 0.469 amps, right? Sorry, that's, no, 0.469 was our power factor. 3.91 amps. So I know my current is 3.91 amps. I know the resistance of the resistor, that was 6 ohms. So if I did 6 times and let me just confirm that, 6 ohms, yep. Right, so power in the resistor would be 6, that's the resistance, times the current squared, I squared R. So current would be 3.91 amps, we have that here. Square that, multiply by 6, should give us the same result as we've got here. Or we could do it this way, S times power factor, so we've already worked out S, there it is there. 195.5 times 0.469 gives us a power of 91.7 watts. Our reactive power then, now we are using I squared R. I squared, in this case R would be our inductive reactance, right? Because we're working out our reactive power, so we need to use our reactance. So I squared being 3.91 squared times 11.31, that's our XL that we worked out earlier, equals 172.9 VAR. And then these three answers here are the three sides of my power triangle. Example number 3. A 5 ohm resistor is connected in series with a 300 millihenry inductor. Remember, this is millihenry, so we're going to need to convert those if we're using them in an equation. 300 millihenry inductor into a 50 hertz supply. We need to calculate the value of the capacitor required to give the circuit a power factor of 0.5 lagging. Okay, so we're going to now work out what capacitor am I going to put in that circuit to make my power factor 0.5. Presumably, we're going to start with a power factor that's worse than 0.5. Well, what do I have to do first? Well, first I'm going to need to work out what the current power factor is. There's no way I can tell how to change that power factor from whatever it is to 0.5 if I don't know what the current power factor is. How am I going to work out the current power factor? Well, power factor would be Actually, so I'm just looking at the working out there. I think we might be doing this a different way. But power factor would be the ratio again of apparent power to true power, or impedance to resistance. So if I worked out what the impedance was, then I should be able to work out what my power factor is. In this equation, what we've done though is we've gone with the new power factor. So if I want the power factor to be 0.5, and I substitute that value into this formula here, so impedance equals resistance over power factor, or power factor equals resistance over impedance, because that's the same as true power over apparent power. Power factor equals R over Z, so therefore Z equals R over power factor. It's just a, what's that word that we use? I can't remember the word. Transposition, there we go. Transpose the formula to get Z, because we were looking for Z. We know what the power factor we want is 0.5. We know what our resistance is, it's 5 ohms. So that means Z equals 5 over 0.5, it's 10 ohms. Now what does that Z represent? That Z represents the impedance required for me to have a power factor of 0.5 with the 5 ohm resistor that I have in the series, in the circuit. So it doesn't tell me anything more at the moment. All that tells me is I need an impedance of 10 ohms. Okay, so then let's have a look at what's our current reactance. XL equals 2 pi FL. So 2 times pi times 50, because that's my F, my frequency, times 300 millihenries. Remember, we're going to convert that, so it's going to be 0.3 henries, or 300 times 10 to the negative 3, if we want to do it like that, equals 94.25 ohms. That's my current inductive reactance. So if my current inductive reactance is 94.25 ohms, I know what my Z is, what my Z wants to be. I know what my resistance is. I know what my inductive reactance is. So now I should be able to use this formula here for impedance. I've got that, that's 10 ohms, that's what I want. I've got this number here, the R, that's 5 ohms. I've got this number here, that's my inductive reactance. The R and the X aren't going to, XL aren't going to change. I just need to add in some XC to make this formula into 10 ohms, to make it make sense for Z. So what am I going to do? Well, I know those 3 variables there. I don't know this one yet. I need to work out what that is. So we're going to transpose that formula to make it about XC. So XC will equal XL minus square root of Z squared minus R squared. Might be a good idea to remember this formula. So if I work that out, XC equals 94.25, that was my XL that we worked out, minus square root of 10 squared is my resistance, minus 5 squared is my impedance, 10 squared minus 5 squared, which means my XC is 85.59 ohms. So what we're saying there is, in order to get this power factor to be 0.5 lagging, I need a capacitive reactance of 85.59 ohms. 85.59 ohms. Now what does that mean? Well, what size capacitor? Well, we don't know yet. We need to work that out. We're going to use the formula for capacitive reactance. We already know the capacitive reactance. That's the capacitive reactance we want. We know what pi is. We know what the frequency is. We've been given that's a 50 hertz supply. But we don't know what C is. We don't know what the capacitance of our capacitor will be to give us a capacitive reactance of 85.59 ohms on a 50 hertz circuit. So we use this formula, but again we'll transpose it. So we've transposed it to make it about C. Capacitance equals 1 over 2 pi F capacitive reactance. So then I'd simply substitute in my values. 1 over 2 times pi times 50 times 85.59 being the capacitive reactance. And it gives me a value of 37.19 microfarads. So that tells me that if I wired a 37.19 microfarad capacitor into this circuit here, the power factor will be 0.5. I realize that probably doesn't sound particularly clear. I will go through some more examples. I might do another video with examples. I will also set you some examples so you can have a crack at that. Alright, example number 4. Current taken from a 115 volt 60 hertz supply is measured as 20 amps with a lagging power factor of 75%. So power factor 0.75. Calculate A, the apparent power, B, the true power, C, the reactive power, D, the capacitor required in parallel to correct the power factor to 95%. Change the power factor from 0.75 to 0.95. Okay, what do we know and what can we find out? So first is it A, apparent power. What I got? I've been told I've got 115 volts. I've been told that the power is, the current is 20 amps. So I can work out my apparent power. That's easy. 115 times 20. That's my total voltage times total current. So my apparent power is 2.3 kVA, kilovolt amps, or 2,300 volt amps. My true power then is easy to work out because true power is a ratio of apparent power. Power factor is a ratio of apparent power and true power. So I just reverse that formula to make it about true power. So P equals S times pi power factor. S is 2,300 times 0.75. My true power is then 1.725. How do I work out my reactive power? Well, now I've got two sides of my power triangle. I've got my S, that's the hypotenuse. I've got the P, and that is one side of my power triangle. Here's the Pythagoras calculation for my power triangle there. Apparent power is equal to true power squared, or square root of true power squared, plus reactive power squared. I just changed that formula around to make it about reactive power. So it would be reactive power equals square root of apparent power squared minus true power squared. Apparent power squared, we have that number there, apparent power, we have true power. I square both of those, and I've got a value of, well, wait, where did it go? There, sorry, it's at the bottom. Yeah, cool. 2.3 kVA squared minus 1.725 kilowatt squared. Take the square root of that number, and I get, every time I go to the bottom of that slide, it puts that thing on there. There we go, Q, if you look at the bottom, Q equals 1.52 kVAR. So now I've got apparent power, I've got the true power, I've got the reactive power. Now I just need to work out the capacitor required to bring that power factor from 75% to 95%. Let's have a look. So for a 95% power factor, my true power is 1.725 kilowatts. That's not going to change. What I want to change is the ratio of true power to apparent power, because that's my power factor. So I would work out this equation again for apparent power with a power factor of 0.95. That's what I want. So 1.725, that's power, divided by the power factor 0.95 equals an S of 1.82 kilovolt amp. So that's that's what I want my apparent power to be, to give me that 95% power factor. Remember, apparent power at the moment is 2.3 kVA. I want it to be 1.82 kVA. So how am I going to do that? Well, I need to add in a capacitor to bring that total, to bring the reactive power down, so that the apparent power will come down. So let's then work out what our new value of reactive power will be. Well, we know what our new value of apparent power should be, and we know what our value of true power is, and that won't change. So I can just use Pythagoras again. Reactive power will equal apparent power squared minus true power squared. So the Q equals 1.82, that's my new apparent power. 1.82 kVA squared minus 1.725 kilowatt squared equals a Q of 580 VAR. So the capacitive VAR required will be where are we? So the additional capacitive power that I need to put in there will be the new Q minus old Q. If we look over here, we'll see, wait for that thing at the bottom to go away again. We worked out our reactive power. Our current reactive power is the Q at the bottom, 1.52 kVAR. So that's this. Wait, something's the wrong way around. It should be that 580 VAR. That'll be our new VAR. 1.52 is our current. So we want 940 additional VAR, additional capacitive power, to bring our 1.52 kVAR to 580 VAR. So our capacitive, our reactive power is going to be V squared divided by XC. To make that about XC, because that's what I need to work out, I know what my QC is. That was for 940 VAR, and I know what my voltage is, it's 115. I can keep that 115, I don't have to work out the voltage across the capacitor because I'm putting it in parallel. So XC will equal V squared over Q, which will give me a value of 14.01 ohms. And then we simply do the same as we did in the last one. I take that equation for working out capacitive reactance, I swap it around. I already know the capacitive reactance, I want to work out the C, so I swap the C and the XC around, and my formula will be capacitance equals 1 over 2 pi frequency times capacitive reactance. Frequency is still 50, capacitive reactance is 14.01, and so the required capacitor will be 227 microfarads. Okay, if you're confused about that, I would recommend going back in this video, go through those examples with your calculator, write it down as you go. I mean, you know, you're not going to win or lose, you're not going to get the right answer, the answer's already there. But if you do that process as I talk through it, it's probably going to make it easier for you to understand. Don't worry, next video we'll go into a bit more depth. Okay, power factor correction methods. So here's a little diagram of what active power, reactive power, and available active power looks like. So power factor correction means changing the power factor to make my circuit more efficient. So getting a better power factor, so we can add components into the circuit to improve the power factor. So we've got passive power factor correction. This method uses passive capacitors and circuits to improve the efficiency of the circuit. This is achieved by placing a power factor correction capacitor directly across the terminals of an inductive load. Putting in too much capacitance can cause conditions of voltage spiking and instability. Therefore, power factor is roughly only ever corrected to about 67 to 85%. So we don't want a power factor of higher than 85% because that's going to introduce other problems. Depending on the type of capacitors used, a range of input voltages is accepted. This method has the advantage of reducing the cable size to the equipment and also allows for the capacitor to be switched on and off with the equipment, therefore reducing risk of shocks or damage caused by charged capacitors. So we're putting the capacitor at the load. Motor connections. Because the capacitor supplies the magnetizing current, the reactive load, the cable coming from the source of power only needs to supply the load current, the real load. Cable and other components upstream of the point where the capacitor ties in deliver only the load current to that motor, or the corrected current, and therefore don't need to be sized to handle the magnetizing current of that motor. So this is saying that if I put that capacitor in that circuit, now there's still that increased current, right? That bad power factor current after the capacitor, but coming into the capacitor it's fine. So inside that motor we're still going to have some of those high currents, but we don't have to have our supply cable to the motor doesn't have to be sized to take that into account. Corrected current has been emphasized because the current flow to the load has only been corrected upstream of the point in the system where you tie in the capacitor. So that's back towards the switchboard, back towards the supply. There is no change to the current flow downstream of the tie-in point. So wherever I've put my capacitor down from there, I'm still going to have that additional bad power factor current. Thus, the power factor correction location is key to accomplishing your goal. Note that choosing a power factor correction location at a motor merely corrects the amperage demands on upstream equipment imposed by that motor. An upstream transformer may still be delivering a disproportionately large amount of magnetizing current to other motors. So then you could have capacitors like in your switchboard that correct the power factor for the whole installation. Correcting the power factor at the motor. By applying the correction close to the motors, you are helping everything upstream. This is the most beneficial power factor correction location, but is expensive if not done during initial construction. An added benefit is that when the motor is turned off, the capacitor, which is not needed, comes out of the circuit. So there we have it there. Here is my motor. It's my starter overloads, my starter contacts, fuses, etc. And here is a correction capacitor. Here is a correction capacitor. I want to go as close to the motor as possible. If you think that the supply current coming in there, that's like our apparent power, coming into the capacitor and motor circuit, that's the inductive and this is the capacitive load, that would be reduced. But after the capacitor, so between the capacitor and the motor, we're still going to get that high rating. The motor is still a poor power factor by itself. So after the capacitors, we have not affected that motor rating. So we want to get the capacitors as close. So we haven't affected the power factor after the capacitors. We want to get the capacitors as close to the motor as possible so that we are impacting the current, we're reducing the supply current for the most distance of our circuit. I hope that makes sense. So then we have, we've got other possible connections here on the other side of the contacts, or this would be a different physical placement of the capacitor, but then running cables back to as close to the motor as we can get them. Active power factor correction uses banks of capacitors situated by the supply source to generate power factor correction of over 95%. This is achieved by switching capacitors in and out of the circuit depending on load requirements. This is especially useful in situations where several motors may be switching on and off intermittently. Active power factor correction also markedly diminishes total harmonics, automatically corrects for AC input voltage, and is capable of a full range of input voltage. Since active PFC is the more complex method of power factor correction, it is more expensive to produce an active PFC power supply. However, the total savings to the consumer over a period of time means that the unit will become cost effective. And then we have an example of active power correction. So this is putting banks of capacitors into our switchboard, measuring the power factor at this point of supply in the switchboard, and then adding capacitors or taking them out of the circuit to increase the total power factor of the installation. Precautions. Capacitors may retain a charge long after power is removed from the circuit. This charge can cause shocks, up to and including electrocution or damage to connected equipment. Take care to ensure that any large or high voltage capacitor is properly discharged before servicing the containing equipment. Yeah, be careful with capacitors, team. Okay, your turn. Practice problems. I won't read those out. What I will do is I will copy those as our practice examples, or part of the practice example worksheet that I'll give you. I'll either do that in Canvas or maybe Google Forms, probably Canvas. I'll put these in Canvas for you, so then you can do those problems in Canvas, and you'll be able to see straight away whether you've got them right or not. So we've got 6 practice problems there. I'll put those all into Canvas for you. So next video will be a little bit more on the calculations side of things. Now, in fact, what I'll do, sorry, I changed my mind. What I'll do is I will work through these examples, all 6 of them, and that's what I'll do in the next video. So the next video will be working through those 6 examples one by one, and then I will put into Canvas more examples that are the same as these for you to work out. All right. Thank you, team. I'll see you at the next one.